is lesson 3.3. In our previous lesson, we learned something called the multiplication rule, and we learned how to find the probability of two events occurring in sequence. And we kind of looked for that keyword like and. So what's the probability of drawing a king and an ace? That sort. In this lesson, we're going to learn how to find the probability that at least one of the two events will occur. And this depends on whether the events are what we call mutually exclusive. So I'll start by talking about what that means. But these ones are going to be like, what's the probability that you draw a king or you draw an ace, like one or the other? It's kind of the idea here, and then there's something called the addition rule. That's a big idea for this lesson. Okay, so mutually exclusive. The textbook definition of mutually exclusive events are two events that cannot occur at the same time or that have no common outcomes. Okay, so if you were to look at like a Venn diagram here, event A and event B, if there's no overlap in the possible outcomes, we call those mutually exclusive. If they do share a common outcome, then they would not be mutually exclusive. So here's just an example of a mutually exclusive, pretty like textbook definition, pretty easy example here. Event A, you roll a 3 on the dice. The only outcome for that to happen is a 3. Event B is rolling a 4. The only possible outcome is there's 4. Those cannot occur at the same time. You cannot roll a 3 and a 4 at the same time, unless you're rolling more than one dice. But those would be like mutually exclusive. They don't share any common outcomes, and they cannot occur at the same time. Okay, so that's going to kind of like factor in how we calculate these probabilities, is if they're mutually exclusive or not. So there's nothing you really need to write down for that. Maybe just I put these cannot occur at the same time. These are mutually exclusive. Okay. So that leads us to the addition rule. So this is how we're going to calculate the probability of one event or another event happening. So for this, you kind of look for that keyword or. And to calculate that probability, and we'll walk through like a couple examples, like one using a Venn diagram so you can kind of like visually see where this rule comes from, and one where we actually go through and like check all the possible outcomes and kind of see like why this rule works. But to find the probability that event A or event B will happen, you just simply, don't forget to grab a packet too, in case you want some more homework for tonight. Work day tomorrow on that.
Oh, really?
And probably Friday with looking at those quizzes. We'll see. All right. You figure out what the probability of event A is. Now, this isn't occurring in sequence. It's just this happens or this happens. So we calculate the probability of B happening, and we add those probabilities together. Now, we have to factor in if there's some overlap, and we counted like those possible outcomes twice. So, like, for example, what's the probability of drawing a king or a heart? The probability of drawing a king is 4 out of 52. Heart is 13 out of 52, but I counted the king of hearts twice in that count, right? There was an overlap there. So you have to subtract out the probability of both them happening, because you're kind of essentially like double counting it. However, if the events are mutually exclusive, there is no overlap. This is just 0. So if the two events cannot occur at the same time, you can just simply do the probability of one event happening plus the probability of the other event happening. Mutually exclusive means there's no overlap. That would equal 0. And then we can extend this to any number of mutually exclusive events. So if we had like 4 different events happening, and we want to find the probability of 1 or 2 or 3 or 4 happening, we would just add those probabilities. So I always tell my students, the easiest way to kind of like work through a lot of these problems is look for those keywords of and or. If you see and, that usually means you're going to use the multiplication rule and multiply the probabilities. Okay, so you're finding two probabilities in sequence. If it's or, and you see the keyword or, you're usually going to add. Okay, so let's look at a Venn diagram example just to give you a little visual of where and why this addition rule works. Okay, so our Venn diagram here shows there's 12 students in Miss Garcia's class. The Venn diagram shows the members for the chess club and the math club. How cool would a math club be? I should start that here in all my free time. Note that Keisha is outside the circles since she's not a member of either club. One student from the class is randomly selected. Let A denote the event that the student's in the chess club, and B denote the event that the student is in the math club. Answer each part below, find the probabilities, and write your answer as a single fraction. All right, so A is in the chess club. So I'm looking in this circle here to determine how many members. I have 1, 2, 3, 4, 5 members in the chess club. So the probability that one of them will be selected is 5 out of, how many total students do we have? 12. Okay, that's a simplified fraction. B is the students are in the math club. Oh yeah, there's way more in the math club. That makes sense. Let's count. 1, 2, 3, 4, 5, 6, 7, 8 out of 12. Which can be reduced to 2 out of 3, 2/3. Okay. So this question said, if I were to read it out loud with plugging in what A and B represent. What's the probability that the student is in the chess club and in the math club? Since A is the event, the student's in the chess club and in the math club, and that would be these two students. 2 out of 12, which can be reduced to 1 out of 6. Okay, let's try this next one. What's the probability that the student will be in the chess club or in the math club? Either or. All right, well, let's calculate how many total outcomes here. So that'd be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 would be either or. 11 out of the 12.
Would you count the ands though?
Yeah, because technically they're still in one or the other. Good question. Yep. Basically, the only one that's not in one or the other is Keisha. So you could also do like the complement if you want. 1 minus everybody who's not in either. 1 minus 1 out of 12 will give you 11 twelfths. So basically, here is my addition rule. I could get this 11 twelfths. I could get this probability of A or B by taking my probability that event A is going to happen. So that was 5 out of 12. Plus my probability that B is going to happen. I'm going to write that as 8 twelfths just so it's easier to add. And then we have to minus out the 2 that are in both that we essentially double counted. Because we counted them in our 5 count for the chess club. And then we counted them again in the 8 that were in the math club. So then you have to subtract out the ones that are in both. And that right there would get you the 11 twelfths, which that's the same that we got for or. So that's basically just showing you the addition rule works. That plus that minus the overlap. Now, if they're mutually exclusive, you won't have an overlap. You essentially don't need to worry about subtracting out the overlap. Okay, make sense? Let's try another one. I like these ones where you can like check the possible outcomes and you can clearly like see the probability. So this time we have 8 balls that are numbered 1 to 8 placed in a bag. Some of the balls are gray and some of them are white, as shown. The balls are also numbered. So 1, 2, 5, 7 are my gray, and 3, 4, 6, 8 are the white. A ball will be selected from the bag at random. The 8 possible outcomes are listed below. So obviously our possible outcomes would be drawing the gray 1, gray 2, white 3, white 4, gray 5, white 6, gray 7, white 8. Check the outcomes for each event. Then enter the probability of each event. Okay, so the ball is selected white. So on my possible outcomes, that would be this ball, this one, this one, this one. 4 out of 8. So the probability of selecting the white ball is 1/2. Okay, the ball selected has an even number on it. 2, 4, 6, and 8 would be my possible outcomes for that. So another probability of 1/2. Okay, here's some keywords, and I even italicized the keywords for you. What's the probability that the selected ball is white and has an even number at it? All right, so we need to check the ones that are white and are even numbered. So I'll just start with the white ones. Okay, so that'd be 4, 6, and 8. 3 out of 8. All right, last one. The ball selected is white or it has an even number. So that would include all these, the white ones. Could be white or it could have an even number. So that would include 2. That would be 5 out of 8. Okay, so basically here's your addition rule. So the probability of A happening is, I'm gonna again do the common denominator one. So 4 out of 8 plus the probability of, oh no, B happening, which is my second row. Uh-oh. Oh no, this one's brand new. No, it's not. This one's my old one. I just broke a marker. No. RIP. Drop it again. Yeah. It scares me. All right, I'll make sure.
Shut up.
All right, I try that more often. Okay. It's fighting. It's fighting. Okay. Drop it again.
She was thinking about it.
I was. All right. 4 out of 8 for B. Minus A and B. So that's this one. Minus the 3/8. Do we agree that that would also give us that 5/8, which is the same as A or B happening? Yes.
Yeah.
Okay. So just a couple examples. I don't really want to call them like proofs, but just to like show you how the addition formula is calculated and like why we have to subtract that out, because we essentially double counted those outcomes. Got it? Okay. So we're just gonna try a few examples, really. Oh yeah, I do want to introduce you to like a notation later on. But we're basically just gonna kind of look at now some probability types of questions where we use the addition rule. So again, you're looking for like those keywords of like and or when we're doing these. So a lot of them, obviously, on your 3 homework, you're going to use the addition rule. A city planner surveyed 130 residents. For each, the planner recorded whether the resident owns a car and whether the resident lives alone. The results are summarized in the table below. Suppose a resident from the survey is chosen at random. Answer each part. Do not round, intermediate computations, and round your answers to the nearest hundredth. Okay, what is the probability that the selected resident lives alone?
No. 37 over 130.
Good job. So there's 37. I'm going to write it like this, but actually I don't want to confuse you with the addition rule. 37 out of, how many total were there?
130.
130. Okay, that as a decimal, my friends, is 0.28. Okay. Pretty straightforward. B. What is the probability that the resident owns a car or lives alone? Keyword. So what's the probability that the resident owns a car or lives alone? Okay, so basically here's how I think of it. I gotta find the probability that the person owns a car. Well, actually, you don't really need to use the formula, but we can. Let's do it. Plus the probability that the person lives alone minus the overlap. Minus the probability that they do both. And then we can go up and use the table and like show an easier way to basically do this. Okay. So probability that they own a car would be this number right here. 21 out of 130. The probability that they live alone, we just had that 37 out of 130. So which one did we essentially double count? The probability of both car and alone is at 7. Yep. Okay. So I got this fraction, 51 out of 130. Rounded to the nearest hundredth, I got 0.39. You could have also done this by just like counting the ones that fall in this category. So the ones that own a car or live alone would be like this one plus this one plus this one, right? You could also do it that way. You don't have to use the addition rule. You could have just literally been like, well, how many own a car? 21. Or live alone. Well, there's 30 that I haven't counted yet, and that'd still get you to that 51. Does that make sense? That's not right. This number?
Yeah.
You got from doing what?
No, I'm saying that is what I
Oh, okay, good. Phew.
got.
Okay. Mr. Chen is about to give one of his students a piece of candy for asking a good question in class. Wow, what a nice teacher. I never do that.
Who is Mr. Chen?
He's going to choose a piece of candy at random out of a bag he brings to class. The following pieces of candy are in his bag. He has 9 apple gumballs, 8 grape gumballs, 10 apple suckers, and 10 grape suckers. What is the probability that the piece of candy Mr. Chen chooses is apple flavored or is a sucker? Okay. So the probability that it's apple or a sucker. I'm just going to abbreviate it like this. So I want to calculate the probability that it's an apple sucker. Probability that's apple. Add that to the probability that it's a sucker. Subtract out the probability of both apple and a sucker. So essentially double counting them. Okay. So the probability that I choose an apple flavored candy, well, I have 9 apple gumballs and 10 apple suckers. So that out of how many pieces of candy do I have? Does it tell me? 37, thank you. Add up all the candies. Plus the probability of having a sucker would be 20 out of 37 minus the overlap. There are 10 apples and suckers out of 37. Again, I know some of these like easier examples, you probably don't need to use the formula. You could literally like count which would fall into that category, which one would be apple or a sucker. But this again just kind of shows you that this formula for the addition rule works. All right. $29 out of 37 to the nearest hundredth. he has a 78% chance that that piece of candy he's grabbing is either going to be apple flavored or it's going to be a sucker.
Ooh.
So again, you could have done this, guys, by just taking like the possible outcomes. 9 plus these 10 suckers plus these 10 suckers, and you could still get to your 29. Okay? I'm just showing you this, so when it gets to harder ones, that would be like the way we'd have to calculate it. And sometimes it depends on like the data we're given. They don't always like list out the outcomes for you. Sometimes they give you like the statistics of it, and you have to use this formula. Like the next one. Here they don't like tell us the number of people who ordered the whatever this is, onion and sausage pizza or whatever. So it says at a certain pizza parlor, 48% of the customers order a pizza containing onions, 35% of the customers order a pizza containing sausage, and 67% order a pizza containing onions or sausage. Or. Find the probability that a customer chosen at random will order a pizza containing both onions and sausage. Okay, so here's I'm thinking my addition formula. The probability that a pizza contains onions or sausages is equal to the probability of ordering a pizza with onions plus the probability of the pizza containing sausage minus both. Okay, here's kind of the weird part of this problem. This is what we're trying to find. We're trying to find the probability that they'll order onions and sausage. That's what that's saying. We know that the probability that the pizza will contain onions or sausage is 67. I'm going to write it as a decimal. And we know the probability that the pizza contains onions. What is that? 48% containing onions. So here's one. You can't add up all the possible outcomes because they don't give us the numbers of pizzas. They give us the probability. So we have to use this addition rule. Plus, all right, 35% containing sausage. Here's my unknown that I'm trying to solve for. If you want to substitute it in with a variable like x and think of it as an equation that you need to solve, you can do that. I started by adding these two together. That gave me 0.83 minus both. Okay, so I kind of like added this one over. And then subtracted that one over. So 0.83 minus 0.67 is 0.16. Okay, so I like that one. We use the addition formula to help us solve an and problem. Okay. Oh, here we go. Here's a notation. So Alex uses this, it's called like set notation. Your textbook doesn't use it, but I think you might see it come up a lot. And like I said, if you ever are working on Alex and sometimes with the explanations, they use this symbol. So I just wanted to go over what they mean. And they're not hard. And you'll have to tell me. I don't think you've probably seen this notation before. Yes, you have. If you talked about Venn diagrams in other classes.
I saw it in that calculus thing you had me in the beginning of the year.
Oh, really?
Yeah.
Nice. All right. So if we want to represent like the union of two sets, so basically it means like this set or this set. So if I said set A or set B, we call that the union. Everything included in both sets. The symbol we use for this is it looks like a U, and we read it out loud as union. It just looks like this. Have you guys seen that before? Okay. So that means the union of both sets. The key words that usually means union is or. So everything in set A or in set B. Okay, so if you look at this Venn diagram as an example, the union of these two sets would be everything in both. 1, 2, and 3. Because it could occur in one or the other. Kind of like with the chess and math club we looked at. How they could be in this one or this one, and technically still the ones in both count because it's either or. Okay, intersection. If we're talking about just what's common or shared in both sets, something like this, we use the symbol that's an upside down union like this, and that's read as intersection. So how I always tell my students to remember it, obviously this one looks like a U, and this one kind of looks like an N, like intersection. And the key word for this one is and. So which students are in the chess club and the math club? They'd be the ones that are in both. That's shared. So in this little example, the intersection of those two sets would just be 2. Okay, complement we've learned. So I've seen this notation on Alex, and then I saw this notation in your book. So kind of the key word for this is like not. The complement is everything that's not in that set. All right, so if I said everything or the complement of set A, it would be everything that's not in that set, that bubble. So that would be like 3 and 4 is technically not. This is an example of a complement. All right, and then these don't come up a whole lot, but in case you see this symbol, the complement of a union, we would still do the union notation. And to do the complement of that, we put it in parentheses and do like an apostrophe. Or again, it could have that line above it. Those both mean complement. So think about what union means. Union means everything in set A or in set B. So the complement is everything not in set A or B. So looking at my union, what possible outcomes 1, 2, and 3, everything not in there would just be 4. Complement of the intersection. Intersection notation, complement notation. How you read that out loud, you can say the complement of A intersect B, or you can say not A intersect B. So again, think of what intersection means, what they share in common. So the complement is everything that's not that. So that in this case, that'd be 1, 3, and 4. Okay. So let's try a couple example problems in Alex where they use that notation. Suppose that A and B are independent events. Okay, we talked about that in the last lesson. That means that the first event does not, the outcome of that does not affect the probability of the next event happening. So like a really easy example is like if you draw a card and then you replace it and then you draw again, that's independent because you're replacing it. So what you did first does not affect your probability of selecting something else. Dependent would be if we don't replace it. So what I draw, now my probability of the second event depends on what card I drew and did not replace. Okay. Independent events, so then we have to factor in like the conditional probability if they're dependent. But here they're just dependent. The probability of A not happening is 0.1, and the probability of B happening is 0.6. Find the probability of A intersect B, or now we can think of this as A and B. Also find the probability of A union B, or A or B is how you could read that. Okay, so when you see this notation, that one looks like an N, so think and or intersection. And this one looks like a U, union, or. Okay, so if they're independent events, to find the probability of A and B happening in sequence, we use the multiplication rule. We calculate the probability of A happening times the probability of B happening, and we don't need to factor in the conditional probability because they're independent events. All right, my only issue here is I don't know what the probability of A is. It wasn't given to me. I know the probability of B happening is 0.6. But I only know the probability of A not happening. So if the probability of A not happening is 0.1, any idea what the probability of A happening is? 0.9, exactly. They have to add to 1. Nice. Oh, they're so excited. That's adorable. I'm going to put them in parentheses so you know how to multiply. Okay, everybody know why we're multiplying here? Because we're trying to find the probability of like the intersection, this and this happening. So we multiply 0.54. Okay, one or the other. Now we use our addition rule. We're going to take the probability of A plus the probability of B minus the overlap, which we just calculated. I'm going to use my symbols A and B, which we just calculated. There is an overlap here. 0.54 is the probability that A and B is happening. All right, so the probability of A, 0.9. Oh, I forgot this one doesn't work. I use that one a lot. Plus the probability of B happening minus the double counting or the overlap. And I got 0.96. Okay, I guess we might as well just finish. We got 10 minutes. Let's just finish the notes, and then we don't have to do notes tomorrow. How about we do like an activity tomorrow, and then since Friday is a short period, we can do weekly on Alex. How does that sound?
Awesome.
I like it. Earth Day.
I will put money on it gets canceled.
Oh, I hope so.
Our,
'Cause I'm doing
the
test that
last
day.
real Earth Day cleanup we've had is 8th grade. Was 8th grade was the
Wasn't
last
this like
normal
3 years ago?
Earth Day. Because freshman year was canceled.
Oh, our 8th grade year, freshman.
Then last year we
And
didn't
sophomore
even
year,
do it.
Probably do it. Yep. Yeah.
Was that our
Hopefully
freshman
it's
year?
out. I want to do it. It sounds
My
fun.
last normal was 8th grade.
I thought it was our sophomore
No, we
That was
in
COVID.
quarantine.
year. Oh yeah.
Oh, remember those good old quarantine days?
Yeah,
Those are the
I
best.
actually miss it really much.
Yeah, that was
A
literally
lot.
the best.
Like I was so active.
Year
I
of my
walked
life.
2 miles every day for gym
Oh,
because we had to
nice.
track our heartbeats. You know,
Yeah. Good times.
actually it wasn't awful. It was really nice.
It's just like life slowed down. I feel like I appreciated the little things and
Yeah.
got closer with my family, got closer with Grant. It was a great time. Made you like realize like big picture things. Like why am I so busy all the time?
Yeah.
It was nice. A lot of self-reflection time.
It was honestly.
Mm-hmm. Okay, let's crank these out. 2 more.
That was
Let B and C be 2 events such that the probability of B is 0.54, probability of event C is 0.3. Do not round your responses. Determine the probability of B union C,
Oh,
or think of that as or. Probability of B or C, given that B and C are mutually exclusive.
so there's nothing here.
No overlap. Good. Meaning that this, the intersection, is 0. There is no overlap. So for our addition rule, we can simply just do the probability of B plus the probability of C. If you wanted to still write minus the probability of both, but there is no. So this is how that, in that very second slide, or third slide, maybe, whatever. If the events are mutually exclusive, it said the addition rule can be simplified to this, where you don't have to subtract that out. Okay, and these were given.
Bliss. Bust out. So.
Okay. Nice. This one is kind of like the last one. This time we don't know if they're mutually exclusive. We just know that they're independent. Okay, that doesn't mean that there can't be overlap. That just means that the outcome of the first one does not affect the outcome of the second one. So I still want to find the probability of or, but basically what I'm going to have to do first is figure out if there is an overlap. Okay, so I'm going to have to find first, is there an intersection here? And just like we did on the last one, since these are independent, you can just do the probability of B times the probability of C. So if you do that math, 0.54 times 0.3, you see that there is an intersection here, or an overlap of 0.162. So when I go to calculate or my union, I gotta do the probability of B plus the probability of C minus the probability of both, which we just calculated. Because this one we don't know is mutually exclusive. That was only for part A. All right. B is 0.54. C is 0.3 minus the overlap, and you get 0.678. Okay, we're gonna try one more. Another mutually exclusive one. Okay, A and B are mutually exclusive. Suppose event A occurs with a probability of 0.65 and event B occurs with a probability of 0.01. So again, mutually exclusive means no overlap. Or A and B is 0. Or, draw a picture. Here's A, here's B. And this kind of helps you actually for the next one. Compute the probability that B occurs, but A does not occur. Find the probability that B occurs and A does not occur. I'm going to do not A. Since there's no overlap, so it's probably this happening and not this happening, it would just be the probability of B, since these are mutually exclusive. There's no shared space here. So probability of B is just 0.01. Okay, that's all I had to do for that one. I don't know if I love this picture, because technically to calculate, well, this is what we should say. This is, I guess, fine. So the probability of A not happening would be all this, right? So what's the probability of not A and B happening? Is just this space that overlaps both. Okay, so it's probability of B happening and not A would just be this space right here. Probability of B. Maybe that is a good visual. Okay, last one. Compute the probability that neither the event A nor the event B occur. Okay, so not A, that neither that and not B. Okay. So you basically just have to calculate the probability. Oh wait, this should be or. Sorry, or. So we just have to calculate A or B not happening. That word nor means or. Okay, so I just did 1 minus the probability of that happening to calculate the probability of it not happening. And since these are mutually exclusive, this piece is easy to calculate. You just find the probability of A plus the probability of B. So to find the complement, we're going to do 1 minus that. Okay, probability of A. 0.65. Probability of B. 0.01. All right, so you'd add those together to find the probability of either or happening. 1 minus that to find the complement. I got 0.34. So basically, we just calculated this space. A or B not happening is all this. Okay, now none of my markers want to work. Oh no. A or B not happening. So I found this. A or B happening, 1 minus that. Okay, that's a wrap. Poor Kyla and Allie. That's a long video. Bye. Bye, everybody.